for the Honda to be 16.3 seconds. And since his T initial was 0, T final is 16.3 seconds. Now let's do the same thing for the Porsche. 400 meters is equal to X initial, which is 0, plus V initial, which is 0 delta T, plus 1/2 times 3.50 meters per second squared, delta T squared. So 400, when I solve for delta T squared, I get delta T squared be 229 seconds squared. Solve for delta T. I get 15.1 seconds. So the initial time, delta T, is equal to T final minus T initial. So I'm going to take delta T plus T initial. I have 15.1 seconds is equal to T final minus 1 second. So I got to add 1 second onto it. T final for the Porsche is 16.1 seconds. So the Porsche still wins by 0.2 seconds. Okay? Now, the thing to understand about this problem is that you had to do 2 identical problems and then do a head-to-head comparison. Okay? Now, the last problem I want us to look at is problem 19. It's one of my favorites. Hint, might want to pay attention to this one. It says that a car starts from rest at a stop sign. It accelerates at 4 meters per second squared for 6 seconds, coasts for 2 seconds, and then slows down at a rate of 3 meters per second squared for the next stop sign. How far apart are the stop signs? Okay, let's draw in everything we know. So I'm going to call stop sign 1 x equals 0. And then there's going to be an x2 position. And between there and the x2 position, okay, he starts out from rest here. V1 is equal to 0. Then I'm going to have a V2 here. I know between here and here, the acceleration is 4 meters per second squared. And then I'm going to make that positive. And our t here, our time, is 6 seconds. Okay? Then I've got another section of travel to get to an x3. And that x3 happens at 8 seconds. Okay, I'm going to be at a V3. During that time, it says it coasts. The acceleration is 0. And then it says that from there to stop sign 2, which I'm going to call x4, the acceleration here is a minus 3.00 meters per second squared. Now, I know that it's 0, even though 0 is not part of the way it's written in the word problem, because it tells me it slows down. Okay? And the velocity final here is going to be 0 because it's going to stop there at that stop sign. But it doesn't tell me anything about the time. So the time here is unknown, the position is unknown. Okay? Now, I've got all of the information that was given to me in the problem in a pictorial form. During position x1 and a position x2, between 0 and 6 seconds, I have uniform acceleration. So I can say that x2 is going to equal x1 plus v initial delta t plus 1/2 a delta t squared. So I can say 0 plus 0 times delta t plus 1/2 times 4 meters per second squared times 6 seconds squared should give me x2. So 6 squared times 4 divided by 2, that gives me 72 meters. Okay, so I now know what x2 is. Now, the next portion, we're coasting. The velocity v2, well, no, we're told that we're coasting. We're told the velocity, no, we're just told we're coasting. So I also need v2. v2 should equal v1 plus a delta t. So that's going to be 0 plus 4 meters per second squared times 6 seconds. So 4 times 6, that's going to be 24 meters per second. So I know v2 is 24 meters per second. I just calculated that. I know x2 is 72 meters. We just calculated that. Now during this section, I am coasting. So that means x final is going to equal x initial plus v delta t. So x final is going to equal the 72 meters plus the 24 meters per second, and the time is 2 seconds. So 24 times 2 plus 72, that means that x3 is 120 meters. 3 significant figures. Now, since I was coasting, v3 is the same as v2, 24.0 meters per second. Now, I know v final is 0. So I can use v final equals v initial plus a delta t to allow me to get my time. So I can see 0 is equal to 24 meters per second plus a minus 3 meters per second delta t. So I have minus 24 meters per second equals a minus 3 meters per second delta t. So 24 negative divided by 3 negative, I get delta t is equal to 8 seconds. So I've got delta t, 8 seconds. And now I can use my initial velocity, my acceleration, and my time to figure out what my final position is. Okay, or I could use, there's a couple of ways to do this. I could use v final squared equals v initial squared plus 2a delta x. I'm going to use that one. So I have 0 squared equals 24 meters per second squared plus 2 times the minus 3 meters per second delta x. So 24 squared divided by 2 divided by 3. I've got delta x to be 96.0 meters. So x4 is 120 meters plus 96.0 meters is 216 meters. Okay? The other way we could have done this would have been to say x final equals x initial plus v initial delta t plus 1/2 a delta t squared. And x initial would have been 120 meters to start that section. V initial would have been 24 meters per second. Delta t was 8 seconds. Plus 1/2 times a minus 3 meters per second squared times 8 seconds squared. We should get the same answer. So 8 squared times 3 divided by 2, I make that negative, plus 24 times 8. Hold on, it's 8 seconds. Delta t was 8, that would, yeah, the delta t was still 8, but 8 plus 8, this would bring it at 16 seconds. So 8 seconds plus 120, I get the same thing, 216 meters. Okay, so 2 different ways that I found it. Now, I really like this problem because it gets you to think about breaking the motion up into pieces and how a very simple motion diagram with information put in on it can help guide the way that you solve a problem. Okay, so that's very important to your progress through a problem. Now, we're ready to look at a classic example of uniform acceleration. Okay? And you're going to do a quickie part of the experiment in lab with this, and we'll come back and do some more detailed experiments with it. But in our first lab, which you'll do before you see this, is going to have just one little quick example of free fall in it. Okay? So free fall is an object moving in one dimension, 1D, under the influence of gravity and only gravity. Okay? So, this is when an object is dropped. Or an object is thrown straight up. Free fall occurs once the object leaves the hand. Now, to be in true free fall, the object would have to be in a vacuum so there is no friction. But, okay, as long as we're not dropping or throwing up to a very, dropping from a very high distance or throwing up from a very high distance, we can assume that an object that is thrown straight up or dropped straight down over a short distance is undergoing free fall. So if I take my golf ball here and I drop it straight down, and when it bounced up, once it got away from the floor, it's in free fall. So I throw it up, comes down. The up and down part, while I'm not touching it, the floor's not touching it, it's in free fall. Okay? Now, when an object is in free fall, it has an acceleration due to gravity. Okay? So the acceleration due to gravity on the Earth has a symbol of lowercase g. And g has a magnitude of 9.80 meters per second squared. Any object that's in free fall is going to have an acceleration of this magnitude. G, the acceleration vector, that's just its magnitude, always points toward the center of the Earth. Okay? It always points down toward the center of the Earth. So, you know, if this was the ground, okay, center of the earth was down here, and I was looking at this object, its acceleration vector is going to point in that direction. If I have an object and it's on this slope, okay, acceleration of the second image, if the center of the earth is here, the acceleration vector is going to point down like that. Okay? So, a free fall problem is a uniform acceleration problem. And we're working in the y direction. So y final equals y initial plus v initial y delta t plus 1/2 ay delta t squared. V final y squared equals v initial y squared plus 2a delta y. And I can say v final in the y direction equals v initial in the y direction plus a delta t. Well, ay delta t. And ay is always equal to minus g, or minus 9.80 meters per second squared. Okay, so those are our equations for free fall. Now, we're going to look at a couple of free fall problems. Okay, let's look at the end of the chapter, and we're going to look at problem 20 on page 60. All right, so let's erase, give ourselves some room to work here. 20, page 60. Now, if I read problem 20, it says ball bearings are made by letting spherical drops of molten metal fall inside a tall tower, called a shot tower. They solidify as they fall. If the bearing needs 4 seconds to solidify enough for impact, how high must the tower be? So we're going to start up here at a y initial. We're going to end down here at a y final. And y final is going to be at location 0. Y initial, we don't know. But I know we're dropping it. So v initial is going to be 0. V final, we don't know. I know that t initial is 0. And t final is 4 seconds. Those are all the pieces of information that we're given. Okay? So we need to find out what y initial is. There's a lot we don't know here. The other thing we know is that the acceleration here is a minus 9.80 meters per second squared. Now, I know a final position, I know an initial velocity, I know t final, t initial, and I know acceleration. So if I start thinking about my equations, I probably want to avoid something that contains v final y, although I could calculate it. One way that you could do this, well, there's a couple of ways I can do this. I can say that y final equals y initial plus v initial delta t plus 1/2 ay delta t squared. When I look at this equation, I go, I don't know velocity, I know velocity initially, I know the acceleration, I don't know this, I know this, and I know delta t. So I could use this. I could go 0 equals y initial plus 0 times delta t plus 1/2 times a minus 9.80 meters per second squared times 4 seconds squared. So 4 squared times 9.80 divided by 2. So I have 0 equals y initial minus 78.4 meters. So I get y initial to be a plus 78.4 meters. Now, if you hadn't thought about doing it that way, you could have solved for v final, because you know v initial, how much time in the acceleration, and then you could have used the v final squared equals v initial squared plus 2a delta x. Okay? But this is a one equation shot. So that's problem 20. Now, part B of the problem says, what is the bearing's impact upon velocity? So this was A. Part B of the problem. I want v final. Okay? Well, it's very easy. I can say that v final equals v initial plus a y delta t. So v final is going to equal 0 plus a minus 9.80 meters per second squared times 4 seconds. So 4 times 9.80, make it negative. I get a minus 39.2 meters per second. That negative sign says that the ball bearing was traveling down, which is what we would expect because we dropped it. Okay? Now, let's look at problem 21. Same page. Okay, if we look at problem 21, no, wait a minute. I skipped over in my notes from problem 20 all the way to problem 80. So let me look at 80 and see if I want to skip all the way over there today. Let's see. Let's look at problem 80. I like problem 80. Now, problem 80 is on page 63. Okay? It says, a rocket is launched straight up with a constant acceleration. 4 seconds after liftoff, a bolt falls off the side of the rocket, and the bolt hits the ground 3 seconds later. What is the rocket's acceleration? So the rocket starts here at the ground, okay, sometimes t equals 0. And it comes out to a point here, and it's got an acceleration, I'll call it a sub r for the rocket. Okay? Now at this point, a bolt, I'm going to draw the bolt over here with a B in there, comes loose from the rocket. Now that happens at